So remember how I said that there's all these different ways for you to calculate the tangential and normal components of acceleration, and maybe I'd get to it in the video, and maybe we talk about it in class. Yeah, I made it all of about 5 minutes after finishing that last video thinking, I really have to tell you how they match, because I don't really like giving you this black box of, oh, poof, and here it is. It's magical math. Math is not magical. Math is logical, and I want you to see the logic. So now I'm going to get amped up talking about why these things are equivalent, and we'll see how far we go. Full disclosure, I am starting this video right now to just try to get it done, and I have not practiced this ahead of time. So there may be mistakes in here, but I'm going to leave it and not edit it for 2 reasons. Number 1, I'm lazy, and I ain't got that kind of time. And number 2, I want you to understand that sometimes math is messy, and sometimes everybody makes mistakes, including me. So we're going to work through it. Okay, I'm going to calm down a little bit. So I want to start with the first one here, and I'm going to look at this first row that says the tangential component of acceleration is first defined as the derivative of the magnitude of the velocity vector valued function. And I want to make sure that makes sense to you. So if I'm talking about the tangential component of acceleration, that means the acceleration in the direction that I'm going. And the velocity really should point in the direction that I'm going. So if I want the acceleration in that same direction, but I want the component, I want the length, it would make sense to use the length of velocity and then kind of take the derivative of that length. So that's really what kind of sets the stage here. So I'm going to take this as fact and say that tangential component of acceleration is the derivative of the magnitude of velocity, because it, kind of makes sense. Derivative of velocity gives you acceleration, all right? But what doesn't make sense is how does that first thing equal the second thing and the third thing? That's what we're not sure about, and that's what we're going to get to. So what I'm going to do first is I'm going to say, let's call my path r of t f, g, and h, where f, g, and h are all functions of t. So f has components f of t, g of t, and h of t. And then if I wanted to take the derivative of r to find the velocity, the vector valued functions for velocity and acceleration, I would have f prime, g prime, h prime, f double prime, g double prime, and h double prime. That seems reasonable. Okay, now, derivative of the magnitude of velocity. All right, well, the magnitude of the velocity vector is going to be the square root of the sum of the squares of the components. So that's going to be f prime squared plus g prime squared plus h prime squared. And I know that kind of looks like a 12 there, so let me give this parentheses. Okay, that looks a little bit better. Okay, and I want to take the derivative of that. So dt of f prime squared plus g prime squared plus h prime squared to the 1/2, because the square root would be the 1/2 power. If I take the derivative of that, I'm going to need the chain rule. So I am going to bring down the power, keep the inside. I'm going to also set me to do not disturb here. H prime squared to the negative 1/2. So there's derivative of the outside, keep the inside. Now I need times the derivative of the inside. And since f, g, and h are all functions, I need a chain rule in here. So the derivative of f prime squared, g prime squared, and h prime squared is going to be 2f prime times f double prime. So 2f prime to the first times f double prime, and then plus 2g prime, g double prime, plus 2h prime, h double prime. Okay, and I have this 1/2 out in front, and I have all these 2's over here, so I'm going to distribute the 1/2 to my 2's, and I'm going to get that. Okay. Well, let's see. What does that look like? I'm pretending I know what it looks like. But what does this look like? Well, what I could also do with this is you say, you know what? If that's to the negative 1/2, now I have f prime squared plus g prime squared plus h prime squared to the negative 1/2. Isn't that really just the magnitude of v on the bottom? Because we said the magnitude of v is right here. It's f prime squared plus g prime squared plus h prime squared square rooted. So I got the magnitude of v on the bottom. And then if I look here, I have f prime, g prime, and h prime multiplied by f double prime, G double prime, and H double prime, well, that'd be V dotted with A on top. And if I zoom back out, I just proved that those two things are equivalent. Cool. I forgot about the second one though. So let's go back here. That second one has the T in it. So I'm going to scroll back here to find that definition of T just so I can pull it up. T is R prime divided by the magnitude of R prime. So if I come back here and I say, okay, how does that match with A dot T? Well, A dot T would be A dotted with R prime divided by the magnitude of R prime. And R prime here, we're calling V. So that's going to be A dotted with V divided by the magnitude of V. And hey, look at that. That's what we had right there. So those three things are equivalent. Super cool. I still maintain that I really would only want to use the first one or the last one when I'm going to take that derivative. But I wanted you to see that they're all the same. Okay. I think part of my yawning, I haven't had my tea yet. I think I'm going to snag all of this stuff. Why can't I lasso this? Nope, not working. Hold on. Lasso this. Gosh, dang it. There we go. I'm going to grab all of this and just kind of move it off to the side. I don't want it to disappear, but I want to move it. And now let's work on row 2 here. All right. So now the normal component of acceleration is the magnitude of V multiplied by the magnitude of T prime. Okay. How am I going to explain that? I think how I'm going to explain that is I'm actually going to start at the end here. So one of the ways I defined your tangential and normal components of acceleration is that they are both constants, okay? And what you really have is if you have the tangential component of acceleration and the normal component of acceleration, okay, what you're going to get is the magnitude of your regular acceleration vector right here. So however long your tangential component is and your normal component is, the right triangle created by your tangential and your normal component of acceleration is going to get the magnitude of your acceleration vector valued function. Okay, so that's the definition of these two. If you formed a right angle with them, the hypotenuse would be the length of your acceleration vector. And if I scroll back up here, I have that right here. Okay. So this right here is really the definition that's going to set us on the right path. Okay. So what am I going to do with this? How am I going to explain everything else? Like I said, I hadn't really planned this out ahead of time, so you're going to let me think through it and hear me talk through it, because this is how math works, folks. When you guys go to college, your professors do not have all the time in the world to explain these things, and you're going to have to sit in your dorm room or, at home and try to figure out, oh, God, how am I supposed to connect these? I don't know. So let's figure it out. Right. So I have these two things, and they lead to that. And so A sub n is really like a backwards Pythagorean theorem where I do hypotenuse squared minus the tangent that we're assuming we already have squared and square root it. I mean, that seems appropriate. So where can I go from here? Well, I could say that we have the square root of the magnitude of A squared. Okay, well, the magnitude of A squared would be the magnitude of A but without the square root, and that was F double prime squared plus G double prime squared plus H double prime squared. So the magnitude of A squared would really just be f double prime squared plus g double prime squared plus h double prime squared. So there's the magnitude of a squared minus a sub t squared. Okay, and a sub t we had over here, all of this was a sub t. So if I did a sub t squared, I could, do I want to use this? Do I want to use that? Let's see. I think I want to use this. So I'm going to come back over here and say a sub t is that mess squared, which is really going to just be f prime squared plus g prime squared plus h prime squared on the bottom, because if I square this piece, it'd just be to the -1. And then if I square the other piece, I really end up with f prime, f double prime, plus g prime, g double prime, plus h prime, h double prime. That stuff is all going to be squared. Okay, fine. Well, now if I want to simplify this, I kind of sort of want like a common denominator, right? And so if I really want a common denominator, I'm going to give this the denominator of the right-hand side. So I'm going to take this and I am going to rewrite it as everything over f prime squared plus g prime squared plus h prime squared. Okay, and in my numerator, this would still be here. Oh, I put my primes backwards. Not that it matters, but... So that's still here. And then up here, I have f double prime squared plus g double prime squared plus h double prime squared times the denominator that I needed to give it, which was f prime squared plus g prime squared plus h prime squared. Okay. And now, if I think about multiplying that through, I think with this subtraction, some things are going to cancel out. Except that's going to take a while. So how do I want to do this? I think I am going to pause the video for a moment, if I can, and I'm going to do it so it shows up and then you can see it happen, all right? So I'm going to pause this video, and when I come back, you'll see what I've done. Okay, I'm back. So what I did was I multiplied through, I distributed this parenthesis times that one, and then I squared this. So this top line is the first distribution, all the way down to there, and the bottom line is the second distribution. Okay, so this part right here, I ended up putting on the bottom. And then I said, you know what, f prime squared, g prime squared, h prime squared, I'm going to call that the magnitude of v again. This square root does extend all the way down there. And so what I have here is I have some things that cancel. Here's f double prime squared, and it's down here too, and I'm subtracting. So these first couple components completely disappear. And then I'm left with the rest of this stuff down here. And what we're trying to match up is we're trying to match this disgusting thing that I just created with this right here. Well, I have the square root of the magnitude of v squared. So if I want, I can take this square root, shorten it to the top, and get rid of that squared. So I'm partway there, and now all I need to show is that this, when I do this difference, is going to be v cross a. So if I can show that this remaining stuff is the magnitude of v cross a, I'm in a really good spot. So let's talk about v cross a, and then I promise I will let this video go because we're already inching up on 15 minutes, and I know that's incredibly overwhelming. So I'm going to come and take this v cross a and put it down here. So v cross a is going to be g prime h double prime minus h prime g double prime. And then it's going to be the negation of f prime h double prime minus h prime f double prime. And then it's going to be f prime g double prime minus g prime f double prime. Okay. And if I were to take the magnitude of that, I'd be doing the square root of the sum of the squares of the components. Now, if you're thinking what I'm thinking, which is, dear God, I have more distributing to do, I'm just going to do one of them to kind of show you where I'm headed, and then I'm going to call it quits. So if I have g prime h double prime times h prime g double prime squared, that's really this thing times itself, which is really going to be g prime h double prime squared minus 2 g double prime h prime plus g double prime h prime squared. Does that feel right? That doesn't feel right. What have I done? No, g prime h double prime squared. Then this would be 2 of these. I missed something. My apologies. So this is h. So this times that is g prime g double prime. See, I told you I'd make a mistake. H prime h double prime. And I'm going to have 2 of those. There we go. Okay. So now let's see if I can find these pieces up in this mess. G prime h double prime squared. G prime, here's g prime h double prime squared. Now let's see if I can find a minus 2 g prime g double prime h double prime. I see it. And technically it is a minus because I'm subtracting this whole denominator. Just ignore the bell. And then I need another plus g prime h prime squared. G prime, or g double prime, pardon me, h prime squared. I found it. I'm pretty convinced. This big mess right here, which is going to be under a radical, is v cross a. And then my denominator is the magnitude of v. So, holy Moses, we got from here to there. Hooray! I'm going to call it quits right there because this has been a long time. But what I want you to get out of this video, besides a headache, is I want you to see that you can prove these things. But what you have to do is you have to kind of create like a fake setup for yourself, like let's call this. Remember let statements? I basically made a let statement and then let the dominoes fall and saw what happened. So I am going to stop there. I feel pretty good because I got through some interesting mathematics. If you're feeling like you want to keep going, by all means, see if you can prove that these other two are equivalent to what we just did. And that's it. Okay? You're done. I hope some of it made sense to you, or at least you understood how to proceed in the future. I am signing off now. Have a great day, everybody.